Oxy-fuel welding gases produce a high-heat, high-temperature flame by burning a fuel gas mixed with pure oxygen. A combination of oxygen and acetylene is the most common type of oxy-fuel welding gas. The oxy-fuel cutting process is used more often than any other oxy-fuel process. But to use the process effectively, it's important to understand how the equipment works. In this program, we'll look at how to safely set up oxy-fuel welding equipment for welding, brazing, soldering, and cutting.
These guys out in our shop, we're custom metal fabricators. At the end of the day, can say, I made this with my own two hands. And sometimes it's very complex and very complicated work. So there's a real sense of satisfaction at the end of the day that I did something. I didn't just push one pile of papers from here to there. A lot of people don't get that. They don't really see the fruits of their labor. So it's rewarding in that respect. Even I get a thrill going out sometimes and seeing the stuff that we've done, or ride by the jobs and say, hey, we did that, and we did a really first-class job.
In this video series, we'll examine the equipment setup for 3 oxy-fuel processes: welding, brazing, soldering, and cutting. All of these processes use the same basic equipment and a fuel mixed with oxygen. The most commonly used fuel gas used with oxygen is acetylene. When acetylene is combined with oxygen, the process is referred to as oxyacetylene welding, cutting, or brazing. Oxyacetylene fuel gas produces a high-temperature flame, which makes it the best gas for welding. But it's also commonly used for cutting and brazing. Another common mixing fuel is MAP, or methylacetylene and propadiene. This mixture is known as OXYMAP. The OXYMAP flame is ideally suited for cutting and brazing. OXYMAP gases don't produce the concentrated flame heat that's required for most oxy-fuel welding jobs. Other fuel gases such as propane and natural gas can also be used for brazing and cutting, but since they produce a lower temperature flame than acetylene, they don't work well for welding. Oxy-fuel equipment setup remains the same no matter what fuel gas is used. But there is one significant safety factor that must be considered when working with acetylene gas. Acetylene can be unstable when it's highly pressurized. For that reason, it's never used at pressures higher than 15 psi. But since it isn't necessary to pressurize oxygen beyond 15 psi when welding, brazing, or soldering, oxygen can also be set at a low pressure. Oxygen is a major component in all oxy-fuel welding processes. Oxygen is a clear, odorless, colorless gas that supports combustion but does not burn. Oxygen is supplied in a high-strength steel cylinder. A fully charged oxygen cylinder is generally at about 2,200 pounds of pressure. Always be careful when you're working with high-pressure gases. An oxy-fuel portable system requires 2 gas cylinders, one for oxygen and the other for acetylene or another fuel. The oxygen cylinder is usually taller and thinner than the fuel cylinder. Both oxygen and acetylene cylinder valves must be protected when not in use. This is usually done with a valve cap. Acetylene cylinders are first filled with a porous material. Then, acetone is poured into this absorbent material. The cylinder must always be upright while in use. A pressure regulator is attached to each cylinder. The regulators reduce the high pressure in the cylinders down to a usable level. This is called the working pressure. An oxy-fuel system setup includes a hose assembly that consists of a pair of hoses molded together. The green hose is used for oxygen. The red hose is used for the fuel gas. The fuel gas fittings are left-handed to prevent the hose from being mistakenly connected to the oxygen side of the system. Oxy-fuel torches that can be used for welding, brazing, and cutting are referred to as combination torches. The torch is designed to have either welding brazing tips or a cutting head attached. Let's go through the safe setup procedures that you must follow anytime you put a system together. First, you need to secure the cylinders so they can't be accidentally knocked over. Cylinders are often chained into a portable cart. With the cylinders secured, you can remove the valve protection cap from the oxygen cylinder. Dust may collect inside of the cylinder valve during shipment, so the dust must be blown out. Be sure the valve is not pointed at anyone or toward anything flammable. Take the oxygen regulator and check that the fitting is clean and that the threads are not damaged. Use your fingers to thread the regulator into the oxygen valve. Hold the regulator at an angle that will make it easy for you to see the gauges on the regulator. Tighten the fitting with a wrench. Remove the valve protection cap from the acetylene cylinder. Make sure that the valve is not pointed at anyone or toward any possible source of ignition, so you can crack the valve safely. The acetylene regulator may have either internal or external left-handed threads. Install the acetylene regulator and hand tighten the threads. Hold the regulator gauges at an angle that will allow them to be easily read, and tighten the fittings. Since oxy-fuel systems use highly combustible fuel gases, they must be designed in a way that minimizes hazards. If the oxy-fuel mixture inside the torch tip becomes hot enough to ignite, it can create what is known as a backfire. When this occurs, a loud pop or series of pops can be heard. A severe backfire can cause a condition known as a flashback. A flashback occurs when the flame burns back inside the system. Often, a flashback makes a whistling sound. A flashback can also be caused by gas flowing back into the wrong hose. The flow of fuel gases in the wrong direction is called a reverse flow. Backfires and flashbacks can be caused by a number of factors, such as incorrect torch adjustment, overheating of the tip, an improperly sealed torch tip, a reverse flow of gases, and a dirty torch tip. A reverse flow can be caused by lack of reverse flow check valves, an empty cylinder, a dirty or plugged tip, improper purging of the system during shutdown. All oxy-fuel systems must have some type of protective device installed to prevent flashbacks and backfires from getting back to the regulators or cylinders. There are two ways that flashback and reverse flow devices are designed. One design attaches the safety device to the regulator, and the other attaches it to the torch. Sometimes both flashback and reverse flow protection can be provided by a single device. This is called a combination flashback reverse flow valve. This type of protection is so important that some manufacturers are incorporating these devices directly into the torches. Protective valves are built into the torch body, so it's not necessary to install them separately. Let's complete the hose attachment procedure. Finger tighten the fitting on one end of the green oxygen hose to the fitting on the oxygen regulator. Tighten the fitting with a wrench. Now we'll install the red acetylene hose fitting the same way. Remember that the fitting is left-handed.
It's extremely important to make sure that all fittings are free of grease and oil. Why? Because grease and oil are fuels, and when these materials are exposed to the compression associated with high-pressure oxygen, heat is created. And in some instances, this heat can cause a dangerous explosion to occur.
Pick up the torch body and locate the fitting for the oxygen hose. It's marked with the term Oxy, or O. Finger tighten the oxygen hose fitting. Don't use a wrench on it yet. Finger tighten the acetylene hose fitting on the torch fitting marked ACT, or F for fuel. Both fittings are finger tightened first because the fittings are very close. Using the wrench could damage the threads. Having both fittings attached prevents this from happening. Once both fittings are attached and finger tightened, it's time to tighten them with a wrench. A welding tip or cutting head can now be installed on the torch body. With the welding system assembled, let's turn on the cylinders and test the system for leaks. Before turning on the cylinder valves, make sure that the regulator adjusting screws are turned out. If the adjusting screw is not turned out before pressure is turned on, the regulator diaphragm can be damaged. Stand behind the cylinder while you slowly open the cylinder valve. Regulators are designed to withstand the high pressure of a full cylinder. But if the regulator is damaged, then it could burst and cause an injury. Turn the oxygen valve all the way on. Oxygen valves have seats at both the top and bottom of the stem. This keeps the high-pressure gas from leaking around the stem when the valve is open. Turn on the acetylene valve no more than one full turn. Some acetylene cylinder valves do not have hand wheels, so they require a special tool called a key or cylinder wrench. If a key or cylinder wrench is required, it must remain on the cylinder valve stem while the cylinder is on. Before a system is pressurized, it must be purged of air. To purge the system, first open the oxygen valve on the torch. Make sure it points away from anyone and that it's not near a source of ignition. Slowly turn in the oxygen regulator adjusting screw until you have about 5 pounds of pressure showing on the gauge. Let the gas flow long enough to make sure that any air has been removed from the oxygen hose. Once the purging is complete, turn the oxygen torch valve off. Now purge the acetylene side of the system just as you did the oxygen side. Remember that the maximum safe pressure for acetylene is 15 psi, so we'll set the acetylene regulator at 5 psi. With the system pressurized, you can check for leaks by first recording the gauge pressures and then turning off both cylinder valves. Watch to see if either gauge pressure drops. A drop in pressure would indicate a leak. After you have allowed time for a potential leak to appear, observe the gauges and reopen the cylinder valves. If, after reopening the valves, the gauge goes up, that could also indicate a leak. If a leak is indicated, spray a leak-detecting solution on the fittings to find the source of the leak. Once the leak is located, try stopping the leak by retightening the fitting. If the leak cannot be stopped, the system is not safe and must not be used. A professional technician trained for repairing oxy-fuel system leaks should be contacted. The system is now ready to be lit and adjusted for use. Because the torch is lit and adjusted differently for different processes, we'll examine that procedure in later programs. Now let's go through the process of shutting down the system. The most important part of shutting the system down is bleeding off system pressure. If pressure is left on, the regulator diaphragm can be damaged. Also, many systems may have leaks that cannot be detected, but can cause problems if the system is left under pressure for long periods of time. Turn off both cylinder valves. When bleeding off the system pressure, do not open both torch valves at the same time. This could cause a reverse flow of one gas into the other side of the system. Reverse flow is the primary cause of flashback. To release the pressure from the system, open the oxygen torch valve. When the gauges read 0, close the valve. Back out the regulator adjusting screw. Repeat the bleeding process with the acetylene side of the system. When both sides of the system are completely bled, shutdown is complete. Now let's review the key segments of the program. 1. Acetylene can be unstable when it's highly pressurized. For that reason, it's never used at pressures higher than 15 psi. 2. All oxy-fuel systems must have some type of protective device installed to prevent flashbacks and backfires from getting back to the regulators or cylinders. 3. Before turning on the cylinder valves, make sure that the regulator adjusting screws are turned out. If the adjusting screw is not turned out before pressure is turned on, the regulator diaphragm can be damaged.